So as we learned today, motion is the topic, and we are starting with the idea that motion is relative, which means that you must compare it to a coordinate system or a frame of reference in order to make it meaningful. And so my question to you is, if I moved 5 feet, or I just shared with you that I'm going to move 5 feet, will you have any idea where I actually will be after that movement?
No, because you didn't say a starting point or an end point, where you were and where you're going to.
Exactly. And so if I say 5 feet, what I have actually described to
No.
you is that there is a 5 foot or a circle with a radius of 5 foot, and I could be along the edge of that circle at any point in that area. And so what I'm going to need to do is I'm going to need to specify where I'm starting and in which direction, based on that position, I am moving in order to make that communication of motion meaningful. So position is compared to an origin. An origin can be like, you have to clarify where your origin is. And that's especially important because if you don't say I'm starting here, then anything you say after that is, just floating. It doesn't have any anchor. You have to anchor your motion to a certain position, to a certain starting position in order to make any following motion meaningful. All right, so here we have a car, and this is what's called a motion diagram. If you will see it later referred to as a motion map, and here in just a minute after this slide, you'll see what the traditional motion map looks like in a particle form. But here we've got it represented as a car. And so the first thing you'll notice is that there's a stop frame, so you can go ahead and assume what's going to happen as this car moves, because this is an animation. But I just want you to watch its motion. All right, so we're gonna rewind that. We're gonna watch that one more time. And so hopefully what you noticed there is that the car had to change its rate of motion as it goes. And so if we look at the stop frame animation at the bottom at t equals 0 seconds, so at the start, we're starting at the origin. So this is obviously where we're starting. And then after 0.25 seconds, we are at this position. You can tell how much space has been changed just by the gap between the two frames. And then at 0.5 seconds, the same interval of time as the original, we have a larger gap, which suggests that we would have moved more space or more position in the same amount of time. And then our final position here, our final stop frame, is at 0.75 seconds, which is the same interval of time. But we notice that our gap in position is going to be quite larger than either of the two previous. And so if we compare all three gaps between 1 and 2, 2 and 3, and 3 and 4, we're going to notice that that gap increases. What would that suggest about the motion of the car?
It's increasing its speed as it goes.
There we go. So this is what we would call speeding up, and it's obvious to you now because you can see that spacing increasing, and the only way to travel more distance for the same unit of time is to increase the speed with which you're moving. And so this is representative of an increasing speed. We'll see a lot more about this with graphs tomorrow or on Friday, but just to let you know, this is what a motion map would look like if you're speeding up. And now we're going to look at what that actually looks like as a motion map. All right, so this is what the traditional motion map looks like. It's just going to be point particles. And so the reason we use particles, especially when we're talking about motion, and once we get to force and newtons, that's really going to be an important point, is the idea that if you have a large, complex body, there's going to be many different factors affecting it as it moves. And generally, especially once we get into the more specific things like torque and kinetic energy and distribution of mass and center of mass and inertia, when we get into the more complex stuff like circular motion, you're going to see that the more complex the example is, the more potential errors that you can make just by neglecting to mention, well, torque here is going to do this, or the fact that most of the mass is out on this limb. So if we're talking about a car, there's fluid dynamics that affects that car. There's friction, there is air fluid friction, which is going to be drag. And we don't want to talk about that. We need calculus to talk about that. We've got algebra to handle this with. So we throw all that out of the window and we call the car this point. Look at that car. That actually solves a problem for many students that can't draw, right? You can draw a dot. You might not be able to draw a car, but you can definitely draw me a dot. And so as long as you can do that, you can represent motion in a motion map like this quite easily. So this is not a complete motion map. We'll look at what a complete motion map looks like probably Friday or next week. But it does give you that idea that each dot represents the same unit time. So the first dot is 0, the next dot is 0.25, that next dot is 0.5, and that last dot is 0.75. So each one of these represent the elapsing of a quarter of a second, and their position along this number line represents their position at that time. So we're going to watch this dot move. Look at that. Look at that dot move. And so as it moved, this would represent a stop frame. So if you took a picture every quarter of a second, this would be the position of that dot as it moved. Excuse me. Now I'm just going to let you know the motion of that, because it's a PowerPoint animation, is not to scale. But this is what it would look like if you did have this motion here. So this is just another way to represent motion that is not a graph and not data and not an equation. This is a pictorial representation in a way. And we will be using these quite often, especially once we get to vectors. All right, and look at that, we're already there, so get ready. So a vector here, if you are in the engineering department, you might be familiar with a vector. But if you're not, then this is a concept that makes describing motion quite simple, because we're going to reduce that motion and the description of that motion to an arrow. We're going to use the length of the arrow or for the magnitude of motion. So if we're talking about a position vector, the longer the arrow, the longer the distance that was traveled. So that's a greater magnitude for a larger arrow. And we're going to use the direction of that arrow to represent the direction of motion. And so vectors are exceptionally important for describing motion graphically or pictorially, because you can just draw an arrow, show that this dog moved to the right by 10 meters, because that's a 10-meter long arrow, and then this dog moved some amount of meters here. So we're going to say that's a 2, and that's probably a -5. So you could find the hypotenuse of that angle. If you knew the angle here, you could find the hypotenuse. You actually, as long as you know the 2 leg lengths, you can find that hypotenuse. And that dog is going to be at this position here. But the fact that we've got a coordinate system makes this have context. Again, motion must be relative to something, which is why we're using this and marking this conjuncture right here as our origin, which is what that 0 states. And then you can then compare where this dog is in comparison to where that dog is in order to specify its location more accurately. So here we look and we can see that, you know, the direction is the same, but that length of the arrow is important because it's representing the magnitude of motion. It's representing just how far that position actually is from the origin. And so both the length and direction of the arrow are important. Vectors are magnitude, or, you know, a number, and direction, which acts like context. All right, so it's motion with context. So now we're talking about vectors versus scalars. And scalars are numbers. Scalars are just a magnitude, just a size, just a value with no directional context. Vectors are a magnitude with a direction. So vectors are a more specific scalar. So can you think of any measurements, and this includes every kind of measurement you can take, that does not come with a direction? It wouldn't make sense to associate a direction because it doesn't depend on space. So can anyone think of a measurement that you could take that would not need a direction and would just be a number of, or just a magnitude?
Temperature.
Temperature, right? What if I told you it's 40 degrees? Okay, so 40 degrees Fahrenheit north. That would not make sense in the context of that. Now we get a little confusing when we start talking about like degrees as in like a 360-degree thing. So that's one of the reasons we use Kelvin in science, and you will actually see that when we talk about heat and energy. So the reason that the Kelvin was invented is because it's the Kelvin, not degrees Kelvin, because degrees is also used as an angle. And so we wanted an absolute scale that started at 0. It's asymptotically at 0. We talked about that when we talked about temperature before. And it does not have the word degree in it. It's actually a unit of measurement, the Kelvin, so that I could say 6 Kelvin and not have to say degrees, so you're not accidentally going to think about an angle. So I saw someone say height, and that is correct. So if you're just talking about height, you're 6 foot. Now, there is technically the implied direction of up, but height as a concept embodies that. Let's get one more. Pressure. So pressure is actually not a scalar. So you might think it's a scalar, but pressure is defined as a force over area, and force is a vector. So anytime you use a vector in a calculation, the resulting calculation must be a vector because the direction mattered for the input, so the output must also have a direction. And inward and outward pressure, if you think about that, that's what determines whether a balloon increases or decreases in size. That's all about direction. That's a good guess though, but pressure is definitely dependent on direction. Let's try one more scalar value. You guys are taking a lot of time to do this. Can you think of any others? Might have just given you a hint.
Time.
Time, there we go, time. Time is unidirectional. So there's no need to specify time's direction, because it's forward, okay? Mass is also a scalar quantity. Volume is a scalar quantity as well. So those two being scalar, density as a result of that is also scalar. So it does not matter the direction of the density because the density just is. Vectors need context. Sorry about that. Vectors need context, which means that you have to have a direction in order for them to have meaning. So let's look at that. This is the first vector we're going to talk about. I believe, yeah. So right here, we have displacement. I want you to notice a few things here. It is described as the change in position, and it is represented as a delta x with an arrow over it. Now, the arrow here is representative of the fact that that is a vector. So you have a vector there. The delta here, if you did not know, that does not mean triangle. It means change. Hopefully you're aware of that. So in chemistry, if you used it in a chemical equation, it would mean adding heat or adding energy. Here, it simply means the change of that variable over time generally. And so when we're calculating that, that's going to be the final value minus the initial value. So anytime we're talking about displacement, you will see it as delta x. That's generally because when we're talking about a number line, that's the horizontal direction, so we associate it with the variable x. So the option they give you is that your first position here is 15 meters, and your second position here is 20 meters. So if you were to move that distance, how would you determine what your displacement was? Well, you would take your final value of 20 and your initial value of 15, and you'd plug it into that formula, and you'd find it to be 5 meters. And now, if I just said 5 meters, is that enough?
I'm going to say no on that one.
Right. So it is not enough because we're talking about vectors. Notice that arrow. So it is important that we know that it was 5 meters to the right, because if I say 5 meters from this initial position without specifying that I'm going to the right, there's nothing that states that I ended up here. I could have gone up down, or backward and ended up back at 10. So that is why we're going to say 5 meters to the right. This is why vectors are important. When we're communicating information about our motion, we have to specify context or else it's meaningless. So we've got two different D words here, and you will really only hear me use one in class, and that's displacement, okay? So the distance, that is just the simple change in position that is context free. It is simply your change in position, and your displacement is particularly where did you end up and where did you start. So it is position dependent. It is context heavy. You have to have context, which means you must have a direction for displacement. Now, I mentioned something earlier, and I said that if the input is a vector, when we were talking about pressure, I said force is a vector. If the input is a vector, then the output will be a vector as well. Keep that in mind as we move forward, because we're going to be using displacement in calculations, and that means that the result of those calculations will also be a vector. So let's click to the next one. Here we go. And so this is, if you've ever wondered, this is the difference between speed and velocity. So the average speed, and I'm going to really hone in on why it says average there, is the total distance traveled over the time it took to travel that distance. Now I want you to remember that distance is not a vector quantity. It is a scalar quantity. It does not care about where you started or where you ended. It only cares about the amount of distance that you traveled. So that means that the resulting average speed is a scalar quantity. I remember this because they both start with S's. Now the average velocity is displacement over time. And so if you remember, displacement was a vector. It's taking into consideration where you started and where you ended. And thus, the result of this calculation here of displacement over time being velocity is also a vector. Now notice you've got V in both words. I accidentally went backward, I'm sorry. So velocity is a vector and speed is scalar. Now I want you to notice that it is average. This is because you can change, like if you've ever taken a trip and you look at a GPS readout, it's going to assume some average velocity is going to take all the roads you're going to travel on. It's going to say, well, you're on the highway for this long, you should be traveling at this speed. Based on the fact that you'll be traveling at that speed and you have to go this distance, it should take this amount of time. It is averaging constantly, even though you will be changing your velocity almost constantly. Even when you have cruise control, if you hit a hill or you start going down a hill, there's a temporary change of velocity as accommodates for that change in gravitational force. And the GPS system tries to average that in. So when we're talking about displacement, this is over a longer period of position change, and you might change your speed within that, or you change your velocity as you go, and the average is just going to be the total displacement over total time. And that's average because it's not going to tell you anything about any given instant. It will tell you that this is what you would have had to keep it on average to make it that far in that amount of time. And we'll look at that in a few. All right. So ignore the answer at the bottom, and I want you to try it yourself. A particle moves according to the equation x is equal to 10t squared, where x is in meters and t is in seconds. It wants you to find the average velocity for the time interval from 2 seconds to 3 seconds. So you should know that if you have t inputs here, you put them into this equation, you solve for the two outlying x's, then you're going to figure out what displacement was, and then you know that the interval of time is from 2 to 3. If you notice on this previous page, we've got a delta t there. That means final time minus initial time. I would suggest you pay attention to that, because otherwise you might end up just saying 3 seconds, which would be incorrect. So if we do that and we plug these values in, we're going to find that T2 is going to yield a 4 here, because 2 squared is 4, times 10 is 40. So our initial position is 40 meters. Our second or final position is going to be 3 squared times 10, which is going to be 9 times 10, which is 90. And so we're going to have ended up at a position of 90 meters. So with a final position of 90 meters and an initial position of 40 meters, we'll find that the change in position, or the delta x, our displacement, was 50 meters. So if we did 50 meters, how long did it take us to travel that distance? And the two times we're looking at here are 2 and 3. 3 minus 2 is 1. 50 over 1 is 50. Notice our units here. We've got meters per second. We've got position change, which is measured in meters, over time change, which is measured in seconds. So that's where our unit for meters per second comes from, and this is our average velocity. This does not necessarily mean you're traveling at 50 meters per second at any given instant. It means that the average of all your velocities would be 50. Go ahead.
Sellers.
Yeah.
So if 2 squared is 4 and then 10 times 4 is 40, right? So the average second, or the change in motion is 40, and then you divide that by 1. How do you get 50? Like, where did
Okay, so you're looking at this first value. So that's going to be your initial position. Then you're going to take the 3 and you're going to plug it in for your final position. And your interval that you're paying attention to is the distance traveled between these two times.
Okay.
So you'll do 90, which is 9 times 10, minus 40. So this is final minus initial, giving you 50 meters. And then you divide by the 1 second that is between these two.
Okay, that makes sense.
Good question. All righty, so now we're going to move on. And we're going to talk about, I just mentioned that your average velocity is just the total average of, that whole section of motion, but it doesn't necessarily give you immediate readout data, right? It doesn't tell you what your velocity or speed was in any given instant during that time. So that is what instantaneous speed and instantaneous velocities are for. So instantaneous speed is a speed at a given instant. The time is very, very small. So technically you can't have, you can make the time interval infinitesimally, let me try that one more time, infinitesimally small, which means infinitely small. And that's an instant. It is the speed that would read out on your speedometer. Your speedometer gives you instant speed. So it gives you instantaneous speed, and as if you watch your speedometer as you take your foot off the accelerator, you're going to watch the speedometer slowly decrease as it slows down. If you were to floor it, you would watch it really quickly jump up, and now it's not the most reactive thing, but it's pretty accurate. Instantaneous velocity is the same concept. It's just a velocity at a given instant, and the time is very, very small. Instantaneous speed is the magnitude of instantaneous velocity. Now, this statement might not make sense initially, but I want to remind you that speed is a scalar quantity and velocity is a vector quantity. So that means that velocity is like speed, which is some change in distance over time, but it's displacement, which means that it has direction as well for velocity. So speed is the number, and velocity would be adding in the direction of motion. So for instance, on the highway, what are those limits called? Are they called velocity limits? No, they're called speed limits, because you can only go forward on the highway. Don't try to go backwards. Don't try it. It's not going to work for you. I don't care if you've seen a movie where somebody turns around and is whipping it through traffic going backward on the highway. That doesn't work, by the way. All right, because not only are you not in full control of the vehicle because you're going backward, you got people who are quickly accelerating toward you, and if you didn't know this, they will actually be, in comparison to you, moving faster than the speed limit, because at that point you're moving backward. So your speed adds to theirs. And so if you were going backward 20 miles an hour and somebody hit you going 65, it would be as if you got hit going with them going 85 and you not moving. So safety concerns aside, you can't go backward on the highway. So that's why you've got a speed limit, because there is only one direction. And also, if they called it velocity limit, everybody's eyes would cross and be like, what's velocity? Because the average person doesn't think about it that way. So that's just a magnitude. It doesn't say forward. It doesn't say north, because the highway constantly changes, right? If you're going on any kind of a road, you don't go unidirectionally. So you have to give it as a speed, which is just the magnitude of the number. So even if you're kind of going in a curve and you're constantly changing your direction, it's suggesting that your speed stay at 35. Now, if it were to be velocity, that would constantly be changing, but the magnitude might not be. Because if you change direction, you change velocity, because you have changed one of the two things that make velocity a vector. All right, if you change magnitude or direction, you're changing your velocity. This is why you have to slow down when you make a turn. If you continue at the same speed and then you hit a turn, you actually will cover more forward distance than you want to, and you'll come off the road, which is why they have yellow signs saying slow down to 30, 35 miles an hour when you're going into a curve. So instantaneous velocity is technically the limit of change of x over change of t as t approaches 0. So I want to remind you that the last slide says velocity at a given instant, time is very, very small. So that means that the interval of time is going to be tiny. And I want to remind you that you can't just pick one time, because the definition of velocity is a change in time. You must have two time values, even if they're so close to 0 that you couldn't tell. There's like 1,000 zeros in front of the number after the decimal point. You still have to have some elapsed time, because otherwise you will not have changed any position. I will remind you, time and position are directly tied. So as t approaches 0, meaning that that interval of time gets tinier and tinier and tinier and tinier, you're getting closer and closer to the velocity at that given instant. So the statement here is that velocity is equal to the limit of the change in position over the change in time, or the change in displacement, as the change in time approaches 0. If you know anything about calculus, this is actually how you would write a derivative. So what this statement is that velocity is the derivative of the displacement with respect to time. That's what this statement states. So if you know anything about derivatives, anything about calculus, that's what this says. And all this means, if you don't know what a derivative is, it's a rate of change. It's the change of one variable with respect to another. So it is a change of rate of one variable when compared to another. So velocity is defined as the rate of change of displacement over or with respect to time. That's why I had to invoke a limit. Limits are the first thing you do in calculus. So somebody that might be in calculus right now, you guys are probably starting to talk about limits. If you did not realize this, calculus as an entire course, or as an entire subject matter, was invented, and I do mean invented, for the purpose of physics. So Leibniz and Newton, which are the two that were working on calculus at the time, both kind of came to the same conclusion around the same time, but Newton gave it the context of physics and actually pretty much pioneered the whole idea of calculus so that he could do physics, which he's the father of, more accurately. We'll get more to that when we get to forces. All right, so instantaneous velocity, or simply velocity, is the derivative of x with respect to t. So that's what I just said a minute ago. So derivatives mean rate of change, also known as, do you know of anything else we've talked about so far that's been described as a rate of change? You guys have known this since algebra 1. Is there anything on a graph that you know of as being described as a rate of change? Slope. So that's exactly the relationship here, which is why we have to know how to graph. Because what do you know? Velocity is the slope of a displacement or position versus time graph, and we'll see that in just a few. So instantaneous speed is the magnitude of instantaneous velocity. That's just a statement, again, stating that a scalar version of a vector quantity. Now we're going to look at graphical analysis of motion, and we're going to talk about particularly position versus time graphs. All right, we're coming in pretty good on time. So right here, and there you go. So there is a distinction here I want you to notice. We were talking about how velocity or instantaneous velocity is the slope, but that is of a curved line. All right, the slope here is average velocity over this interval. So when you have constant motion, meaning that the rate of change does not change, your velocity here is the same the whole way through. So you could very confidently say that this graph right here, slope does not change from, the origin to the last point shown. And in this case, your average is your instantaneous. That means that if you took any given interval of time here and you measured the slope of that change in position in that interval, you would find it would be the same as if you took the beginning and ending value here. This is only true for constant motion, and constant motion or uniform motion is simply described as non-changing velocities, meaning you hold a constant speed. And so here we can see that that's pretty constant. That slope is constant. The only time you will see a constant position versus time graph is if the velocity is not changing. So this is actually an indicator, and we'll get to that later as we move further into the course. So the slope of the line is equal to the average velocity. In this case, does the slope also equal the instantaneous velocity? Well, I answered that for you. Yes, it does, because constant means that any instant is the same as the average. So motion with a constant velocity will have a straight line, and it will go into the same direction, which will look very much like that graph we just saw. Now we're looking at a position versus time graph where you do not have constant motion. So if I asked you without that blue line, what's the slope of this line? What might your answer be? What's the slope of this line?
You
Does
can't
anyone-
find it because, right?
Yeah, so you're completely correct. There is no slope to this curve. Now, I kept calling it a line, but that's not accurate. This is a curve. As you can see, it curves. And we could describe that as a top opening parabola. Oops. And so this top opening parabola here has no single curve or no single slope. The thing about a curve is that it has infinite numbers of slope. So what you would have to do is you could take the total change in position over the total time, and you would get this really crude line that would get you to the end and start at the beginning, but it would not adequately model the whole motion between there. You'd have a picture, and it wouldn't be a good one, but you'd have an idea of how fast you went, but you wouldn't have any given data for each individual point. In order to know what your instantaneous velocity here at any given time, it is going to be the slope of a tangent line. So if you guys remember a tangent, it is a line that touches a curve just once. And the space over which it touches that curve is a tiny fraction of time, which sounds a lot like instantaneous velocity. So you could tell me that the velocity of this line right here, you could measure the slope of that tangent line, and then for this one instant, you could give me an instantaneous velocity. But that would not be applicable to anything before or anything that follows it, so long as we were talking about a curve. So this right here is called instantaneous rate of change, because it's instantaneous velocity, and we're talking about a rate of change because we're measuring slope. Even though an instantaneous change is kind of a irony. It's actually an oxymoron. It shouldn't exist, but that's the best way we have of describing it. So find the instantaneous velocity at 2 seconds and the average velocity from 0 to 2 seconds. So if you went for the average velocity, all you would need is the change in position, which would be 20 meters, and the change in time, which would be 2. So 20 meters over 2 seconds would give you 10 meters per second as your average velocity. So that would be a line with a slope of 10 meters per second that went to right there. Now, if I want to know what the instantaneous speed here, I'm going to have to measure the slope of this line. And so in order to do that, I'm going to project it a little bit. So if I take it from 2 and I projected that line down, I'd say if we look where that cursor is, that's roughly where I'd think 1 would be. Do you guys agree? Somewhere around 1. So let's just say it's 1. And so it goes from 1, this line right here goes from 1, to 2, and it goes from 0 to 20 in that span. So if it goes from 1 to 2, 0 to 20, that means it has a change of 20 over 1 second, and we're going to have an instantaneous velocity at this point of 20 meters per second. Even though the average velocity over this whole interval is 10 meters per second, that's because everything before 2 seconds here, if my final instantaneous velocity right here is 20 meters per second, at no point am I going to be going 20 meters per second before then. So that's just something to note. And now we're going to end on this. This is our position versus time graph, but I want you to notice that it's kind of wonky. The first thing I'm going to point out is that if we look at time 1.5, we've got an impossibility. So if you want, I want you to imagine what would be required for that line that passes through 1.5 to exist. What does that suggest based on your axes?
Teleportation.
Exactly. This is suggesting multiple locations existing in every position from -10 to 20 meters. That is a 30-meter long object or a point particle that's existing every space in between those two. And it's going to let you know that can happen on the quantum scale. Electrons very frequently will teleport. They will exist or occupy 2 states at once. It's called superposition. And I'm going to let you know, this is not the graph of an electron, because an electron cannot move 30 meters like that. They're moving nanometers. So they teleport and jiggle so fast that as far as our detection devices are concerned, we detect them at multiple locations at once. And that's just spooky action at a small distance. But this is simply for graphing purposes to show you something that should not and cannot exist. So if at any point you're graphing and you get that line, you did something wrong, kid. Try again. All right, so let's go ahead and look at what it's asking. At what times was the object at the origin? So go ahead and look at that. The origin is the line that is the x-axis. And we're going to have 1, 2, 3, 4 points at which it's at the origin. And then it asks, what is the average velocity from 0 to 1 second? So let's just start there. 0 to 1 second. So we'll go from 0 to 1 second. So we know our time is going to be 1 second there. So whatever we find our change of position to be will be our magnitude of the velocity. And it seems like it goes, if I were to trace that out, roughly 15 meters in that 1 second. So I'm looking at an average velocity of 15 meters per second. I will remind you that that's actually the instantaneous speed, the entire length of this line, because it is constant. The slope doesn't change. Your velocity won't change either. Now we're looking at 1 to 1.5 second. So we've gone from 1 to 1.5. Now I want you to notice, what's the slope of that line? This one is negative. So you would have a negative velocity, which means you're approaching your origin. All right. We'll get into specifics about what negative and positive velocities look like graphically tomorrow. So we go from 15 to -10. So your final position is -10. -10 minus 15 is going to be a total of 25. And it's negative. So it's a change of -25, and that's denoted by the fact that it went down. So we've got -25, and it does so in half a second. So if I divided -25 by 0.5, what is my average speed here? Anybody?
Isn't it negative 50?
Negative 50 meters per second. You're hauling butt. All right. So this is a very rapid change. And then in this one instant, it's like, hold the phone and watch this. It went from negative 50 meters per second and then instantly teleported 30 meters away in less than a nanosecond. So just instantaneously jumped here. And then it says from 0 to 2 seconds. So it doesn't even ask about this interval. So from 0 to 2 seconds, what's its average velocity? What's your starting position?
There is no velocity.
0.
So yes, so your average velocity here is going to be 0 meters per second. And you might say, hold up, there's motion. We just talked about how this right here is 15 meters per second. That's negative 50 meters per second. If you calculated this out, you'd find it to be even steeper than that. So this is like negative 75. And then this is, it's looking like it's almost parallel with that. So that's probably somewhere around negative 40, negative 45. And somehow I'm over here saying that the average velocity here was 0 meters per second. And why can I say that? That is because if we look at what the definition for average velocity was, it was displacement over time. So the displacement takes into the account the final position and your initial position. So your final position here is 0 meters, and your initial position here is 0 meters. And so you have essentially done a whole lot of work to end up right back where you were. And thus, you have changed no displacement, even though you did travel distance. You traveled many meters, all right? There's 15 there. There's another 25 there. So that's 40. And then we've got another 30. That's 70. And then we've got 10 right there, and then another 10. So we've got 80 meters traveled. So your distance is 80 meters. Your average speed would be 80 meters over 2 seconds. And because direction doesn't matter, you could say that that's an average speed of 40 meters per second. But we're not talking about speed. We're talking about velocity, and velocity cares about where you ended and where you started. So we will see an example tomorrow in a similar PowerPoint that's slightly different that I'm not going to spend so much time on, where you are talking about, displacement versus distance. So I'm going to stop the recording.